The next item to be examined in the ICS computational stack is the control software. So again, that is a software that runs on the real-time operating system that's responsible for the input, compute, and actuation part of the control loop. So PLC can be programmed in various ways. There are programming languages similar to what we know for regular IT software, C, C++, Java. They're programming languages standardized for PLCs, and the standard is IEC 61131. And the languages can be either text-based or graphical-based, visual-based mostly. The ones that currently supported in the standard, and that we'll see today in this module, is ladder logic, function block diagram, structured text, sequential function block, and instruction listing. And there's also another language that's not standardized, but is used by some vendors that is called continuous function chart. So let's dive in and see all these languages one by one. The first one is ladder logic, that, as I said, is a visualized language, and it gets its name from the way it looks like. When you create those rails, they look like a ladder. Ladder logic was initially used to document the design of relay racks. So you can think, so if you look at this, it looks like a rack that on it you can have different relays in series or in parallel to implement the control function. So here in ladder logic, the primary elements are contacts with this notation of the square brackets and the coils that are denoted by the parentheses, and whether they're default open, the default close, these are the way they've been marked. And if you look, these are standard Boolean operators like not. In this way, you have the OR function, like one of the two, or the AND function in series. So here, both of them have to be open in order for the value to propagate. Here, one of the two needs to be open for the value to go through, and here this corresponds to the NOT operator. So correspondence to ICS, you can think of the contacts, the square bracket notation as the sensor input, and the coils as the actuation output. And to see how a sample ladder logic program would look like in a graphical user environment, so here we have a screenshot from Codesys, one of the frameworks that you can develop PLC applications in. And you can see how the program looks like, but this is what you would develop. It's more, again, it's a visualized language. So you have your contact here, you have your coil, again, parentheses, and the square brackets that look like more straight lines here. And you have your logic operation, like an adder in this case, that given an enable signal, it will take the input and it will produce an output and also a down signal. Then again, that can be the output of the actuation. That could be go to LED, for example, as I have here. You can see the three inputs, two analog inputs, 0 to 10 volts. Analog input and analog output, input and output. Enable is a digital input, so 0, 1, 0, 5 volt for 5 volt for 1 for enable button, and the output for the LED indication. So this part is how ladder logic would look like, how you would program a very simple program we have here in ladder logic. Next is function block diagram, that it is again a visualized languages, and the primary elements are these function blocks. So it's a modular design, and you have the function block that every block is implementing a function, as the name implies, and the wires coming in on the left side, these are the inputs to the function, and on the right side you have your outputs. So here, for example, that's a limit function block. It has a minimum, maximum, and input, so it maintains the output within the limits, the minimum and the maximum, and by reading the input and saturating either on minimum or maximum. And you expect to have multiple of these blocks connected to each other, maybe sequences, or you may have some of them in parallel. Going to a similar example, in the same framework we saw ladder logic. this is how it would look like. You don't have now coils and contacts and coils. You have just the block that it receives the input. There's also the enable signal like before, and you have the output and the done signal as output. So you have inputs, the block itself, and output. So it's similar to before, but again, the ladder logic, it resembles more of how a rack would look like. Here, this is more of a design that you have more of a functional design. You have input, function, and an output to produce your control. Third is structured text. So structured text is not visualized like the other two, but it is textual, and it's mostly based on Pascal, and it has a typical imperative programming language syntax. Imperative in the context of programming languages means that the function is operating on a state, and the state, every function contains the state of the machine. So imperative programming languages, they have the variable declaration at the beginning. What are the variables you're going to use in the function? You have your regular if statements, for while loops, and also you can call other functions. So in a way, you can implement more complex logic using structured text compared to the other two, and also it enables modular programming. So many of these functions may come from the vendors. They may provide functions like a PID controller. You can just bring it in as a function, or you may have the saturation counter, you have absolute values, or you may have cosine function, something that again resembles if you program in C++, you bring a standard IO library and you have all these functions that are standardized in C, your scanf, printf, and so on and so forth. So here in structured text, you can do something similar. You have modular programming with libraries, and you program much closer to how a regular program would look like, but there's still distinct differences. Example here, we have the, again, same inputs and outputs. You have your analog input, your analog output, and a digital input, digital output. But here, instead of the visualized, the block we saw before, it's just code. So there's if statement, if enable is true. So input is incremented by 1 and is being fed to the output. So it adds just 1 to the input and produces the output, and it's done. Otherwise, if it's not enabled, then done is false, and that's it. You assign a value to your LED, and that's it. Continuous function chart, or CFC, is a visualized language similar to function block diagram, but this is not standardized under the IEC standard. Still is pretty popular because it's used by industry leaders like Siemens and Codesys. It's again close to functional block diagram in terms of it has a block that has wires on the left and the outputs on the right. But what's different about it is you may have, unlike the functional block diagram, you may have independent block circuits. So in a functional block diagram, you could have one chain that should be fully interconnected. Here, you may have independent ones, and you don't have to have them connected at any point. And there's also an extra property that is priority. So since you have multiple blocks, you may want to define priority as well. So you define priority in each block as a numeric value. So in this example I have on the slide, you can see again a function block that you have your enable and input, but also there's a priority number that will define, if you have multiple of these, it will define what's done first and what's the second, and so on and so forth. So since you have independent chain of events, you can prioritize their execution to ensure that you have a proper flow in your control logic. So these are the languages on how you program your code. We saw examples of simple function that adds 1 to the input and produces an output. But to program them, in regular IT, you would have your IDE, Visual Studio, or some kind of advanced text editor that you type your code, you use a compiler, you compile, and you execute. Here, programming a PLC, you get a vendor-specific API or ID. And typically, it's platform-based. Rockwell is called Studio 5000. Siemens has Step 7. Beckhoff, TwinCat, and Wago has the newest one is the eCockpit environment that allows programming its PLCs. And Codesys, for example, supports more than one vendor. It's more of a multi-platform. Same with OpenPLC. There are multi-platform environments that you can write your code and compile it for different PLCs that support the Codesys platform. So to program PLC, with the exception of structured text, it's more of a drag and drop environment. As we saw, most of the languages were visualized. So you take your function blocks, you bring them into your IDE, to your test workbench, and you connect them. So you bring your absolute function, your minimum function, your limit function, you connect them to wires. And this resembles a typical block level hardware software design. So once you create your control logic, then this is compiled to a custom time binary. It could be directly assembly, or it could be bytecode, depending on how the vendor has implemented their custom compiler. And then once you compile that binary, this can be taken to the PLC to be the control logic to be executed. And on the PLC, you typically have a runtime that will take that binary compiled from PLC language and will execute it. So this is how development would look like in Studio 5000. That's ladder logic, as you can see. The vertical lines, again, looks like a ladder to an extent, but this has way more functions than the simple ones we saw before. So you have in the environment, you can bring your components, drag and drop into your design. You can create your, again, left to right flow of how you have input, processing, and the output being produced. Similarly, in step 7, this is how it looks like. Different graphics, right? But the idea is the same. If you compile something ladder logic in one environment, the same ones, since it's a standardized language, the same one should work on another environment as well. In this example, step 7. OpenPLC, this is an example of ladder logic as well. In that environment, that's, again, OpenPLC is free and free to use, so anyone can experiment with that. And all the languages we saw, and we saw also in the beginning of the class, the PLCs have to be monitored by an HMI. So you have your ladder logic to be loaded to the PLC, and then you have to connect to it and be able to receive information from, about what's happening in the control process. And those HMIs can also be programmed. That's why I have them discussed here, right after how to program a PLC. Within the same framework, let's say Codesys or the step 7 environment, you can create graphical interfaces as well. Or you can take them pre-made for you from the vendor, but you can also create your own. For example, in Codesys, this is a very ugly, but it does the job. You have your analog meters here about what is the final set point you have set. Maybe you have a desalination plant. You have your LED indicators that show you what is the input coming in, and again, what is the output being produced. So you have here, if you see, you have again an inventory of visualization tools that you can use in order to create your own HMI. So this HMI has been created, in the lab, and it's simple to create and simple to interface with the values, the corresponding values in the PLC language, ladder logic or structured text, or the function block diagrams. Similar in step 7, you have your, again, visualized components. You can drag and drop and create your own HMI to be either run on a computer or maybe dedicated touch screens or touch panels that can be in different parts of your process. And once you have your HMI, I have this example. So the Wago PLC runs the HMI, the HMI as a web service on the PLC itself. So to get the status of the PLC, you connect not through Modbus, but through a web server, so the web service HTTP in this case, to the PLC, and the PLC is running that HMI and gives back a visual input to the operator. And that's the benefit of the process is that you don't need dedicated hardware running on the other side. You just need your TCP/IP connection and a regular browser to connect to the PLC, and you have the status of the PLC. So it's very easy to monitor that PLC because it runs its own web server that provides this visualized environment, this HMI that provides the information the operator needs to understand what's happening in the process.